Hi all. This is a quick video to show you the solution to the non-homogeneous system. That is number 3. So if I go up, this is our practice problems from section 5.2 on solving systems by elimination. So on Friday, we worked through the first two, right? And that one and this one, okay? And then I don't think we went over the answer to number 2, but we'll get there in class. But I did want to take you through number 3, okay? And what makes this one different is that it is non-homogeneous. So these values on the right are functions that are not functions of x or y, so functions only of the independent variable. And that makes it non-homogeneous. So the way that we handle this is the same way that we would handle non-homogeneous for a higher order equation, which means we're going to solve the homogeneous version first. So I'm going to do two things to start. I'm going to go ahead and switch to operator notation. So I'm going to turn my primes to d's, and then I'm going to turn the t squared and the 1 into zeros. So we're going to make this dx plus y equals 0, and we're going to make it negative x plus dy equals 0. And we're going to solve this system first. So this goes exactly as the other ones did. So we are going to eliminate a variable. I'm going to eliminate the x first. So I'm going to multiply the top. Actually, I'm not going to multiply the top by anything. I'm going to multiply the bottom by d, or take the derivative of the bottom, is really what you're doing when you multiply by the operator d. And so we end up with dx plus y equals 0 and negative dx plus d squared y equals 0. Now I can go ahead and add these two together. The x's will cancel and we'll eliminate that variable. And we'll be left with d squared plus 1 operated on y equals 0. Now at this stage, we are solving for y. That's the variable that's here. And we don't want our y to be exclusively 0. So that means we want the d squared plus 1 to be equal to 0. And this is just like solving the characteristic equation for your higher order equations. So we're going to go ahead and solve for this. So this becomes d squared equals negative 1 and d equals plus or minus root negative 1, which is your plus or minus I. Okay, well, what does that mean here? What that means is that we're going to get purely imaginary solutions. So we're getting sines and cosines. Your alpha here, the real part, is 0, so there's no exponential term. And the coefficient to the I is 1. So that means that we are going to get that y of t is equal to c1 sine t plus c2 cosine t. Okay, now we should get the same exact thing for x. I'm going to go through it just to make sure, but we should get that x of t is equal to, in this case, c3 sine t plus c4 cosine t. And let's see how that one works out. So from this initial set of equations here, instead of multiplying the second one by d, I'm going to multiply the top one by negative y. So I'm going to turn the top, times negative d. And I don't want that as an x. Let's make it a, whoa, sorry, friends. We're going to multiply by negative d. That'll get rid of my y. Okay, so that's going to give us a negative d squared x minus dy equals 0 for the top equation. The bottom equation we're going to leave as is, so negative, the part that's in parentheses. So negative x plus dy equals 0. Now, when I go ahead and add these two together, the y's cancel. And I'm left with negative d squared minus 1 x equals 0. So now we're solving for the x, and we don't want our x to be exclusively 0, so we take what's in the parentheses, the negative d squared minus 1, and set that equal to 0. And again, this is just like solving the characteristic equation for a second order equation. I'm going to divide everything here by negative 1. And then solve this. We saw this one before. This is d squared plus 1. You subtract the 1 to the other side, take the square root. This is also going to give us d equals plus or minus I. All right, so I'm going to cut a couple steps there because we already did it. Okay. All right, and that verifies for us that x of t then is also sine t and cosine t. So this is c3, so we have new constants, sine t plus c4 cosine t. Okay. Now, these two together have to solve that homogeneous equation, and we still have too many conditions. So we're going to have to plug back into one of those two equations so that we can get rid of 2 of our 4 c's. Okay, and this happens within the homogeneous equation. So all this is part of solving the homogeneous. We'll get to the t squared and the 1 in a little bit. Okay, so next what we need to do is we need to plug into one of those two. I'm going to plug into the top equation. So I want the dx plus y equals 0. So I am taking the derivative of x, and that's going to be c3 cosine t minus c4 sine t plus y, so plus c1 sine t plus c2 cosine t, and that has to be equal to 0. Okay, and then we're going to pull our like terms together. So my sines would be this term, and they're going to have to cancel out. So that tells you that negative c4 plus c1 has to be equal to 0. And if you add c4 to the other side, that tells you that c1 is equal to c4. So they're the same. And then we want to look at the cosine terms. So let's look at this one, c3 cosine t and c2 cosine t. And that's going to give us c3 plus c2 has to be equal to 0 because those two terms, when I add them up, have to go away. And so then let's move the c3 to the other side. So c2 is equal to negative c3. And I'm going to go ahead and replace c1 and c2 with negative c3 and c4. And that means that my homogeneous solution, my xc and yc, if you will, so xc of t, the complementary solution, we're going to keep our c3 and c4, so c3 sine t plus, plus c4 cosine t. And my complementary solution for y, I'm going to replace the c1 and the c2 with my constants from over here. So c1 becomes c4, so c4 sine t. And c2 is negative c3, so minus c3 cosine t. So this solves my homogeneous, so that's the first part. And now we've got to go back and we've got to solve the non-homogeneous part. So I need to choose a particular solution that's going to solve for t squared and 1. Now we know that the interactions, because of the way the derivatives and the constants work here, that we want our form for our xp and our yp, our particular solution for x and y, we want them to have the same format. So they have to cover both the t squared and the 1. And remember that you're typically choosing something that's a generic form of the function that you have. So I want to choose a generic quadratic for both, and I need to have fresh letters for everything, okay, or unique letters for everything. So I'm going to let my xp be equal to a t squared plus bt plus c. You need to go out. And we're going to have d t squared plus, let's skip over capital E just because I don't like it, ft plus g. You can keep with E if you like, totally fine. Okay, now there's a good chance that a lot of these are going to be 0, but maybe they won't be. And so we're going to treat this exactly like we did when we were solving undetermined coefficients for higher order equations. So that means we're plugging back into the original system way up top. So that means I need to know what x prime and y prime are. Okay, so that's fine. We can do that. So xp prime is just 2at plus b, and yp prime is 2dt plus f. And now we're plugging back into that equation. So we have x prime plus y equals t squared. So x prime is 2at plus b, and I'm actually going to line these up vertically, plus y, I think it was, yes, plus y equals t squared. So plus y, so y is going to be d, and I'm going to line them up by power, so dt squared plus ft plus g. And when you add those up, you have to get t squared. Okay, and so what happens is then we essentially, in each column, create an equation. So here, dt squared has to be equal to t squared. So that tells me that d equals 1. Then the t terms have to work out. So 2at plus ft has to be 0 because there's nothing there. So 2a plus f is equal to 0. And then we have this last one, b plus g. And again, that has to be 0 because there's nothing there. So b plus g equals 0. And then we're going to do the exact same thing for the second equation. Okay, so the second equation says negative x plus y prime equals 1. So we're going to do the same thing here. So negative x is going to be negative a t squared minus b t minus c. And we're going to add to that x prime. So that's 2dt plus f. And that all has to be equal to 1. Right, and that's my constant. So I'm going to go column by column here, and that'll tell me what these letters have to be. So first column, negative at squared. There's nothing down there that's a t, so that means I'm going to get that a equals 0, right? Because I have to get no t squared term. Then if I look at the second column, I have negative b plus 2d. And there are also no constant terms down below, so that also has to be 0. And then my third term, the negative c plus f, has to be 1. And now I have 6 equations and 6 unknowns that I should be able to solve. So far I've already got 2 of them. I already have d equals 1. So we've got that one. Check that one off the list. And we have a equals 0. All right, so what I'm going to do is I'm going to bring my a equals 0 over here. So if a equals 0, then 0 plus f has to equal 0, which means that f equals 0. And as I mentioned before, a lot of times these turn out to be zeros. So there's another one. Then let's take the d equals 1 over to here. So that's going to give us, that will turn into negative b plus 2 equals 0. And that tells us that b equals 2 if we add the b to the other side. So there's our fourth variable. All right, now take that b back over to the left. And that'll tell us that 2 plus g is equal to 0. So subtract your 2 to the other side, and you get g equals negative 2. And let's see what's left. Oh, f is 0. So we're bringing this f equals 0 over to here. And that tells us that negative c plus 0 equals 1. Divide that negative 1 over, and we get c equals negative 1. And there's our 6 values. Okay, so we plug those back in to form our full solution. And we're going to do this all in one shot. So we had that x of t was c3 sine t plus c4 cosine t. Right? That comes from our complementary solution in the box. Then we are going to add to that from here, the x of p, xp is at squared. So a is 0, so there's no t squared term. B is equal to 2, so plus 2t. And then c is negative 1, so minus 1. Then we have y of t. From what's in the black box, we have c4 sine t from our homogeneous solution minus c3 cosine t. And then from down here, we want dt squared. Well, d was 1, so that's plus t squared. Let's see, plus f. F was 0, so there's no t term. And g was negative 2, so t squared minus 2. And then this is the full solution to our non-homogeneous equation. Okay. Now then, they could also then give us conditions. Okay, once you've solved the non-homogeneous, if we had conditions for x of t and like x of 0 and y of 0, we could plug that in, and that'll let us isolate the c3 and the c4, and then we have a very unique solution to the set of differential equations to the IVP. But generally, you're following the full procedure to find the homogeneous, which is what we did up here. Then you're making a guess for what the particular solution is going to be, and that guess has to cover everything that's in any part of any equation, any part of your f of t. Okay, so that has to cover the t squared and the 1. For us, that's just a quadratic would cover both. But if you had, for example, an exponential and a t, you need both an exponential term and then a generic linear term for the t. So make sure that you have enough to cover everything. A lot of times, just the way that this works, sometimes you end up with a lot of zeros, which we did. We ended up with 2 of 6 were 0. And then we can put together our full solution. Okay, so take a look at this one. Make sure that that one gets in your notes, and then in class, on Tuesday, we'll get started with where do these types of solutions come up. We'll look at some application problems as to where this strategy is useful.